I'm Jordan Gottdank from Oberlin College, and with Professor Stephen Fitzgerald, we looked at a set of compounds called the metal organic frameworks for hydrogen storage. Particularly, we looked at MOF74, which is originally a carbon, hydrogen, oxygen framework with zinc ions, and we also substituted cobalt and nickel ions with an attempt to see how the changing metal ion in the framework affects the binding energy. So the way we looked at this was through infrared spectroscopy and loading isotherms. Loading isotherms give us a general idea of how much hydrogen in general the compound can store. Infrared spectroscopy, which results here, gives us a better picture of the actual binding energy of the primary or secondary binding sites, which is then in turn useful for designing new materials in the future to store more hydrogen better at more desirable temperatures and pressures. So we can look at the binding energy by looking at the redshift. As the hydrogen that's absorbed goes through quantum transitions because of the infrared light, there's a redshift in the infrared absorption peak, and from that we can get a general linear correlation between the redshift and binding energy, and we can use that to better analyze binding sites.
My name is Ben Thompson. I am actually from Ohio Wesleyan, but I did research at Oberlin with this as well. And as Jordan was saying, finding how the redshift and the binding energy correlate will help us find better materials in the future. We looked at 3 different metals, nickel, cobalt, and zinc, in our MOF. And it turns out that the nickel was the best. It had the furthest redshift, which means it bound hydrogen the best, which means that it stored the most hydrogen per weight, which is what we want to look for. Over here it shows our results for how much hydrogen the MOF can store. We got a value around 2 weight percent. To put that in perspective, the Department of Energy wants us to get up to 9 weight percent. Is the target for successfully storing hydrogen for applications such as cars, things like that. So to start the hydrogen economy, we have to get up to 9%. Right now, we only have about 2, so we clearly have a long way to go. So, in addition to looking at these 3, there are also 2 more compounds we can look at. We can put manganese and magnesium ions in instead of nickel, cobalt, or zinc, and that will also help us determine how much that improves it, and also guide us towards our next goals. Unfortunately, the MOF74 that we looked at can only have a certain number of metals in it, and so we'll have to move on to a different kind of compound next to study. So once we do those 2, those results will help lead us to what we want to study next and what has the greatest potential for storing the most amount of hydrogen. So hopefully we will, in future years, find better materials and get up to that 9 weight percent.